Hello guys, and this is Inside XO from the Earth. And today we're gonna start to learn some new stuff, and which name is reinforcement learning with OpenAI, TensorFlow, and Keras using Python. Okay. Just before this, I just learned a lot of things about Python and TensorFlow and Keras, but now I think it's the time to move to a new era of machine learning to get started with reinforcement learning, which I think may be amazing. For the first, you may say all those items which is unfamiliar for you. Yes, of course, for me too. And don't worry. And all those things we will cover it one by one. So you don't have to worry much about it. Okay, let's get into the introduction. This book is primarily based on a machine learning subset known as reinforcement learning. We cover the basics of the reinforcement learning with the help of the Python programming language and touch on several aspects such as Q-learning, MDP, RL with Keras, and OpenAI Gym and OpenAI environment, and also cover arguments related to RL. RL is a short term for reinforcement learning. Users need a basic understanding of programming in Python to benefit from this book. The book is meant for people who want to get into machine learning and learn more about reinforcement learning. Here we go, Chapter 1, Reinforcement Learning Basics. This chapter is a brief introduction to reinforcement learning and includes some key concepts associated with it. In this chapter, we talk about reinforcement learning as a core concept and then define its future. We show a complete flow of how reinforcement learning works. We discuss exactly where reinforcement learning fits into artificial intelligence. After that, we define key terms related to reinforcement learning. We start with agents and then touch on environments and then finally talk about the connection between giants and environments. So, what is reinforcement learning? We use machine learning to consistently improve the performance of machines or programs over time. The simplified way of implementing a process that improves machine's performance with time is using reinforcement learning, or RL. Reinforcement learning is an approach through which intelligence programs, known as agents, work in a known or unknown environment to consistently adapt and learn based on given points. The feedback might be positive, are also known as rewards, or negative, also called punishments. Considering the agents and the environment interaction, we then determine which action to take. In a nutshell, reinforcement learning is based on rewards and punishments. Some important points about reinforcement learning. 1. It differs from normal machine learning, as we do not look at training datasets. Interaction happens not with data, but with environments, through which we depict real-world scenarios. As reinforcement learning is based on environments, many parameters come into play. It takes lots of information to learn and act accordingly. Environments in reinforcement learning are real-world scenarios that might be 2D or 3D simulated worlds or game-based scenarios. Reinforcement learning is wider in sense because environments can be large in scale and there might be a lot of factors associated with them. The goal of reinforcement learning is to reach a goal. Rewards in reinforcement learning are obtained from the environment. As you guys may see, that this robot and the environment is kind of like a circuit. The robot, if you think it as a human do actions, human take actions which can change the environment. And then the environment gives some feedback to humans. Environment could affect humans. Then humans rely on the feedback, rely on the changes in environment, do things. Okay, it's kind of like a circuit. You do things to environment, you make change to environment. Then, if the environment change, you have to change your actions too. A maze is a good example that can be studied using reinforcement learning. In order to determine the exact right moves to complete the maze. You can see here is a figure about a maze. In this figure, we are applying reinforcement learning, and we call it the reinforcement learning box because within its winsality, the process of RL works. RL starts with an intelligent program known as agents, and when they interact with environments, there are rewards and punishments associated. An environment can be either known or unknown to the agents. The agents take actions to move to the next state in order to maximize rewards. In the maze, the conceptualized concept is to keep moving. The goal is to clear the maze and reach the end as quickly as possible. The following concepts of reinforcement learning and the working scenario are discussed later in this chapter. The agent is the intelligent program. The environment is the maze. The state is the place in the maze where the agent is. The action is the move we take to move to the next state. The reward is the points associated with reaching a particular state. It can be positive, negative, or zero. We use the maze example to apply concepts of reinforcement learning. We will be describing the following steps. 1. The concept of the maze is given to the agent. 2. There is a task associated with the agent and reinforcement learning is applied to it. 3. The agent receives reinforcement for every move it makes from one state to another. There is a reward system in place for the agent when it moves from one state to another. Yeah, it's kind of hard to understand, but okay, it's okay. We will continue to read it, and when we finish reading, we will get a whole concept about this. The rewards predictions are made interactively. Iteratively. The rewards predictions are made iteratively. Where we update the value of each state in a maze based on the value of the best subsequent state and the immediate reward obtained. This is called the update row. The constant movement of the reinforcement learning process is based on decision making. Reinforcement learning works on a trial and error bias because it is very difficult to predict which action to take when it is in one state. From the maze problem itself, you can say that in order to get the optimal path for the next move, you have to weight a lot of factors. It is always on the bias of state, action, and rewards. For the maze, we have to compute and account for probability to take the step. The maze also does not consider the reward of the previous step. It is specifically considering the move to the next state. The concept is the same for all reinforcement learning processes. Here are the steps of this process. 1. We have a problem. 2. We have to apply reinforcement learning. 3. We consider applying reinforcement learning as a reinforcement learning box. 4. The reinforcement learning box contains all essential components needed for applying the reinforcement learning process. 5. The reinforcement learning box contains agents, environments, rewards, punishments, and actions. Reinforcement learning works well with intelligent Reinforcement learning works well with intelligent program agents that give rewards and punishments when interacting with an environment. The interaction happens between the agents and the environments. And from this figure, you can see that there is a direct interaction between the agents and its environments. The interaction is very important because through these changes, the agent adapts to the environments. When a machine learning program, robot, or reinforcement learning program starts working, the agents are exposed to known or unknown environments, and the reinforcement learning technique allows the agents to interact and adapt according to the environment's features. Accordingly, the agents work and the reinforcement learning robot nerds. In order to get to a desired position, we assign rewards and punishments. Now, the program has to work around the optimal path to get maximum rewards if it fails. That is, it takes punishments or receives negative points. In order to reach a new position, which also is known as a state, it must perform what we call an action. To perform an action, we implement a function, also known as a policy. A policy is therefore a function that does some work. A policy is something you maybe could imagine that it's a strategy. Okay, it's kind of like strategy, or yeah, that's it. It's about a way to do things. The phases of reinforcement learning. As you say from this Venn diagram, reinforcement learning sits at the intersection of many different fields of science. The intersection points reveal a very strong feature of reinforcement learning. It shows the science of decision making. If we have two paths and have to decide which path to take so that some point is met, a scientific decision-making process can be designed. Reinforcement learning is a fundamental science of optimal decision-making. If we focus on the computer science part of the Venn diagram, we can say that if we want to learn, it falls under the category of machine learning, which is specifically mapped to reinforcement learning. Reinforcement learning can be applied to many different fields of science. In engineering, we have devices that focus mostly on optimal control. In neuroscience, we are concerned with how the brain works as a stimulant for making decisions and study the reward system that works on the brain. Psychologists can apply reinforcement learning to determine how animals make decisions. In mathematics, we have a lot of data applying reinforcement learning in operations research. Okay, the workflow of reinforcement learning. As you can see, here is the simplest one of the flow, but we can go further. The interaction happens from one state to another. The exact connection starts between an agent and the environment. Rewards are happening on a regular basis. We take appropriate actions to move from one state to another. The key points of consideration after going through the details are the following. The reinforcement learning circuit works in an interconnected manner. There is distinct communication between the agent and the environment. The distinct communication happens with rewards in mind. The object or robot moves from one state to another. An action is taken to move from one state to another. Here is another picture, another diagram. You can see the agent basically combines with two parts. One is learner, another is a decision maker, and he gonna to interacting with the environment and choose an action to the environment. Then the environment responds to an action. This makes the program generated a nuisance, and then the nuisance could somehow return a reward. An agent is always learning and finally makes a decision. An agent is a learner, which means there might be different paths. When the agent starts training, it starts to adapt and intelligently learns from its surroundings. The agent is also a decision maker because it tries to take an action that will get it the maximum reward. When the agent starts interacting with the environment, it can choose an action and respond accordingly. Okay, from then on, new sentences are created. When the agent changes from one place to another in an environment, every change results in some kind of modification. These changes are depicted as signs. Just like game developing, they call changes as signs. Okay, the transition that happens in each step helps the agent solve the reinforcement learning problem more effectively. Let's look at another scenario of state transitioning. Okay, here again is a simplest one. And as you can see, here he just gave us a mathematical formula which shows that if the gamma lesson, if lesson is 0, that means the reward is associated with the current state only. But if the gamma is 1, that means the reward is a long-term reward. It means it always useful or determines the actions. Okay, you may not understand, but you will know it after or when you reading this book after. Different terms in reinforcement learning. Now we cover some common terms associated with reinforcement learning. There are two constants that are important in this case: gamma and lambda. Gamma is common in reinforcement learning problems, but lambda is used generally in terms of temporal difference problems. Gamma is used in each state transition and is a constant value at each state change. Gamma allows you to give information about the type of reward you will be getting in every state. Generally, the values determine whether we are looking forward values in each state only, in which case it's 0, or if we are looking for long-term reward values, in which case it's 1. Lambda is generally used when we are dealing with temporal difference problems. It is more involved with predictions in successive states. Increasing values of lambda in each state shows that our algorithm is learning fast. The faster algorithm yields better results when using reinforcement learning techniques. As you learn later, temporal differences can be generalized to what we call TD or lambda. We discuss it in greater depth later. Interactions with reinforcement learning. Let's now talk about reinforcement learning and its interactions. As shown in this figure, the interaction between the agent and the environment occur with a reward. We need to take an action to move from one state to another. Reinforcement learning is a way of implementing how to map situations to actions so as to maximize and find a way to get the highest rewards. The machine or robot is not told which actions to take, as with other forms of machine learning. But instead, the machine must discover which actions yield the best reward by trying them. In the most interesting and challenging cases, action affect not only the immediate reward but also the next situation and all subsequent rewards. Okay, RL characteristics. We talk about characteristics next. The characteristics are generally what the agent does to move to the next state. The agent considers which approach works best to make the next move. The two characteristics are trial and error search, delayed reward. As you probably have gathered, reinforcement learning works on three senses combined, S, A, R, where S represents states, A represents action, and R represents rewards. If you are in a state S, you perform an action A so that you get a reward R at 10 from T plus 1. Now, the most important part is when you move to the next state. In that case, we do not use the reward we just earned to decide where to move next. Each transition has a unique reward and no reward from any previous state is used to determine the next move. The T change. It means the time frame changes is important in terms of reinforcement learning. Every occurrence of what we do is always a combination of what we perform in terms of states, actions, and rewards. Okay, it may seem crazy, it may seem ununderstandable, but we will cover it later. We will see the whole pictures of this. Just have patience. We will get it. How reward works. A reward is some motivator we receive when we transition from one state to another. It can be points, as in a video game. The more we train, the more accurate we become, and the greater our reward. Agents. In terms of reinforcement learning, agents are the software programs that make intelligent decisions. Agents should be able to perceive what is happening in the environment. Here are the basic steps of the agents. 1. When the agent can perceive the environment, it can make better decisions. 2. The decision the agents take results in an action. 3. The action that the agents perform must be the best, the optimal one. Software agents might be autonomous or they might work together with other agents or with people. Here you say, agent. It's gonna reserve the environment, perceive the environment, and it must take decisions, and the decision will result in action, will affect the action. Let's talk about RL environments. The environments in the reinforcement learning space are comprised of certain factors that determine the impact on the reinforcement learning agent. The agent must adapt accordingly to the environment. These environments can be 2D world or grids or even a 3D world. Here are some important features of environments. Deterministic, observable, disaccurate or continuous, single or mute agent. Deterministic. If we can infer and predict what will happen with a certain scenario in the future, we say the scenario is deterministic. It is either for RL problems to be deterministic because we don't rely on the decision-making process to change state. It's an immediate effect that happens with state transitions when we are moving from one state to another. The life of a reinforcement learning problems becomes either. When we are dealing with RL, the state model we get will be either deterministic or non-deterministic. That means we need to understand the mechanisms behind how DFA and non-DFA works. DFA, deterministic finite automata. DFA goes through a finite number of steps. It can only perform one action for states. See this figure. And now you can understand either of me. So we are showing a state transition from a start state to a final state with the help of a diagram. It is a simple depiction where we can see that with some input value that is assumed as 1 and 0, the state transition occurs. The self-loop is created when it gets a value and stays in the same state. Okay, it's a totally mess. I couldn't understand every single sentence in this paragraph. Non-DFA, non-deterministic finite automaton. If we are working in a scenario where we don't know exactly which state a machine will move into, this is a case of non-DFA. Okay, you can see this figure, but you may not understand. But okay, let's read the following paragraph. The working principle of the state diagram in this figure can be explained as follows. In non-DFA, the issue is when we are transitioning from one state to another, there is more than one option available. As we can see in this figure, from state S0, after getting an input such as 0, it can stay in state S0 or move into state S1. There is a decision making involved here, so it becomes difficult to know which action to take. And for some inclusion, the machine have to determine whether they want to take actions or just stay where it is and don't take any actions. So in this case, it's kind of like human thinking. Okay, human have to decide whether he go or not. Observable. If we can see that the environment around us is fully observable, we have a perfect scenario for implementing reinforcement learning. An example of perfect observability is a chess game. An example of partial observability is a poker game where some of the cards are unknown to any one player. Discrete or continuous. If there is more than one choice for transitioning to the next state, that is a continuous scenario. When there are a limited number of choices, that's called a discrete scenario. Okay, let's talk about the single agent and multi-agent environments. Solutions in reinforcement learning can be of single agent types or multi-agent types. let's take a look at multi-agent reinforcement learning first. When we are dealing with complex problems, we use multi-agent reinforcement learning. Complex problems might have different environments where the agent is doing different jobs to get involved in RL and the agent also wants to interact. This introduces different complications in determining transitions in states. Multi-agent solutions are based on the non-deterministic approach. They are non-deterministic because when the multi-agents interact, there might be more than one option to change or move to the next state, and we have to make decisions based on the ambiguity. In multi-agent solutions, the agent interacts between different environments are animals. No, I don't think so. How to say that? Enormous, okay. Are enormous. The environments are enormous. They are enormous because the amount of activity involved in reinforcement references to environments is very large. This is because the environments might be different types and the multi-agents might have different tasks to do in each stage transition. The differences between single-agent and multi-agent solutions are as follows. Single-agent scenarios involve intelligent software in which the interaction happens in one environment only. If there is another environment simultaneously, it cannot interact with the first environment. When there is a little bit of convergence in reinforcement learning, convergence is when the agent needs to interact far more often in different environments to make a decision. This scenario is tackled by multi-agents, as single agents cannot tackle convergence. Single agents cannot tackle convergence because it connects to other environments when there might be different scenarios involving simultaneous decision-making. Multi-agents have dynamic environments compared to single agents. Dynamic environments can involve changing environments in the places to interact with. Here you can see a picture. It means a single agent. And here is another. You can see two agents, and every agent have its goals, have its actions, and have its domain knowledge, and so on. So as a conclusion for the first chapter, we will say this chapter touched on the basics of reinforcement learning and covered some key concepts. We covered states and environments and how the structure of reinforcement learning looks like. We also touched on the different kinds of interactions and learned about single agent and multi-agent solutions. The next chapter covers algorithms and discusses about how to build in a real reinforcement learning, or what's the blocks looks like to build a reinforcement learning machine or software, somehow, some kind of like that. So I'm very happy to be here to share you guys with this kind of knowledge and this book. So maybe hope to see you in the next video. Bye.